So in solving this problem, we're going to use what is called Green's theorem. Green's theorem Green's theorem is about an integral along, it's about line integrals. So if you have a line integral, and if the line integral is along a closed curve, then the Green's theorem allows you to change the line integral into an area integral, area enclosed by the curve. So let's now, you learned that in calculus. We're going to go over it. So let's consider time tau and theta as 2 times, tau less than theta. And I have an integral from j tau to theta, that is integral from tau to theta of this value here. Okay. And my x dot is given by this. My initial value of x is a, and my value at theta is b. And I have a bound from control from 0 to q. To change this objective function to a line integral along a feasible arc, call it gamma 1, from tau a. Remember, tau a is the point in the beginning, x tau of a, so you have a 2-dimensional tau and a, to theta b in the tx space. We multiply 7.28 by dt and obtain the formal relation u dt equal to dx plus delta x dt divided by r times 1 minus x. We substitute this guy into the objective function 7.27, and we get a line integral. So now we have a line integral along gamma 1. This is our gamma 1. This is our gamma 1. Let's say a curve along the gamma 1. And we want to integrate that along gamma 1. And we want to integrate this thing. But this thing has been converted into, by substituting this, it has been converted to a line integral. And now, you know what a line integral is. You have something dt minus something dx. So that integral is called a line integral. The way you define a line integral is you take a point and you just go, you go an area called dx times dt. So you have a dx by dt area, and you go along dx by dt area along this curve, and you multiply this quantity by dt, that quantity by dx, and you go all the way up to here. And then you change the dx and dt go to 0, you get a line integral. So that's the definition of a line integral. The Green's theorem says that if I have a line integral along gamma 1 and I have a line integral along gamma 2, then notice what is going on. Such a curve can be done by a control u of t. So if I have a control u of t over time from a to b, from tau to theta, if I use that control, I can, using a control, I can see the trajectory in x space. The x space is the trajectory of the market share from tau to theta given a control. So whatever control that's given to me, it will create a path. Okay? And so for that control, that path gives me the profit of that control. So for any feasible control, I can create a path. That path then can be expressed by a line integral, and that line integral basically is the profit of that path. Another control, this is the profit of that path. So for different feasible control trajectory from tau to theta, I can express the profit from tau to theta of any feasible control by by this integral. That means first I take the feasible control. From feasible control, I create a path xt in the xt space, and then that path allows me to define this line integral. And that gives me the profit. So now what happens is if I have one path given by one feasible trajectory, one feasible control trajectory, and I have another path by one feasible control trajectory, then I can compare the profit of those paths by computing the profit of the line integral. Right? That is something I can do. But more than that, suppose I change this gamma to in the other direction. If I do that, then the line integral simply says it becomes minus of the line integral, because the line integral has a direction sense, okay? So when I do the gamma 2 on that side, this becomes a closed curve. It's a simple closed curve, so it's not like number 8. It's a simple closed curve, it's like this simple. We don't have to define topologically, but simple closed curve, you know what it is, okay? It's just this kind of a curve, okay? Then the Green's theorem says that the line integral along this circle or this closed curve is nothing but this area integral. Notice now, this is if I call j gamma 1, this j gamma 1, this j gamma 1, if I call j gamma 1 as the profit of this trajectory, and if I call j gamma 2 to be profit of that trajectory, then j gamma 1 minus gamma 2 means arrow on that side, is the difference in the profit of this trajectory and that trajectory. It's a difference in the profit, so it allows me to do a comparison. That means the area integral of this kind allows me to compare the profit of gamma 1 and gamma 2. Okay, so what am I doing here? So gamma, let gamma be gamma 1 minus gamma 2. So the gamma is this whole gamma. This is the gamma. And this is R, which is the area enclosed by gamma. So let gamma, which is gamma 1 minus gamma 2, because I changed the arrow, is a simple closed curve. And usually the line integral is done in the counterclosed direction. So a counterclockwise direction, then j gamma, which is the integral, line integral along this gamma, is nothing but j gamma 1 minus gamma 2, because gamma 1 and gamma 2 is this gamma. Then that is j gamma 1 minus j gamma 2. Okay? So j gamma, which is j gamma 1 minus j gamma 2, is by Green's theorem, is given by this formula. Okay, the formula is you take, well, the Green's theorem, you take this, they say this is m and this is n, then you take delta m, you take delta m delta x times dt minus delta m delta dt dx. So as you see here, delta t of that quantity so delta t, so this is the line integral, this is the and you see the circle here, that circle means it's a line integral along a simple closed curve. So that is the notation from calculus. So we get a simple closed curve. The Green's theorem says I can convert that into the integral, double integral on R. So the double integral is delta t of this quantity minus delta x of this quantity. So you have delta t of this quantity minus delta x of that quantity dt dx. So that is the formula coming from calculus that says the proof is not very complicated. What you do if you go to calculus back, if proof is, see, remember there is this Line integral is these squares here, right? Those squares, dt dx squares go all the way up to here. And the line integral, there's a dt dx square go all the way up to there. So that's your line integral when you take the limit. And then area integral is you take the dt dx square in the entire region. And so and when that area is given by this. So now we can define the boxes for that integral, and you can define the boxes of this integral, and then you subtract, then you compare those the boxes, and then you take the limit. So that basically, it's a very simple kind of proof that you can go back to calculus and do it. I'm not going to do it. So now we have the formula. We know how to take these derivatives. When you take these derivatives, we get this. So what we have done so far, we have defined a line integral. We have defined two line integrals. If they do in a counterclockwise direction, we have a simple closed curve. We convert them into area integral, and now we have an area integral right now sitting with us. Now what happens? Suppose that area integral, suppose all the terms inside that area integral is positive, then that area integral is positive. Suppose all the terms in this are negative, then that area integral is negative. Suppose I can find all of them are positive, then what happens? It says j gamma 1 minus j gamma 2 is positive. That says that profit at j gamma 1 is better than j gamma 2. That's a comparison. So the comparison says j gamma 1 is better than gamma 2. That means the lower path is better than the upper path. Okay? If it is negative, then it's the other way around. Okay? So we have a basis of comparison that tells you whether the upper path is better than the lower path or the lower path is better than the upper path. That is what we're trying to get now. And this allows us basically to solve the problem, optimal control problem, totally. So this is, I call this to be Ix. We need to find out the sign of this Ix. Remember, if it's positive, we know what to do. If it's negative, we know what to do. Okay? So we need to find the sign of this guy. Well, this is a quadratic equation in 1 divided by 1 minus x. So we know how to solve it. We know how to solve any quadratic equation whatsoever. Okay? And we know the sign of this integrand is same as the sign of Ix. Also notice that this quantity, when x increases, this quantity increases. Because when x increases, the denominator decreases. So as x increases, this quantity decreases. That means that if I can find a quadratic solution, if I can find a solution of this equation by equating it to 0, then above that 0 line, the integral is positive, and below the 0 line, the integral is negative, right? So we know all of that. Okay, so we solve this equation. How do we solve this equation? We solve the equation for 1 divided by 1 minus x, and that gives me that solution by just minus b divided by b squared plus minus 4ac. That's the formula that we do. And then because it's 1 divided by 1 minus x, we can find the x. Okay, that x gives me a 0 value of this integral. Okay, and I am going to define, because this x is a market share, negative market share does not make any sense. So I'm going to define a quantity called xs, which is equal to max of this quantity and a 0. Remember, I don't need to take minus sign here, because minus sign will make this quantity minus minus, and this minus will make this quantity more than 1. More than 1 is not allowed market share. So minus can be easily discarded. So the only solution that is important is the plus solution. And then I only need to worry about that plus solution would not give us a negative value for this first term. So I put 0 here. So we eliminate the solution of x above 1. And by this, we eliminate the solution below 0. So that's our excess. Okay. this is excess. So let me just go one or two slides ahead of us, and what I'm trying to tell you what is going on. This is our excess. So this is going to be turnpike. And to follow the turnpike, I can easily find out the US. US is delta excess R 1 minus excess. So if I'm at excess and follow it, then I also know that I can stay on that solution. Okay, I'll go through all of this later, but just get to you the bigger picture here. And then what happens? Let's not worry about this right now. Let's go here. So we already know that this is excess. This is where the integrand Ix equal to 0. We know that above this integrand, the integrand is positive. Above this line, the integrand is positive. Remember, the integrand increases with x. So if it is 0 here, then it's positive above. And we know that below this line, it is negative. Okay. Now let's look at the following situation. Suppose I'm giving you this, and suppose my x0 is here, and suppose my xt is here. Okay, so what am I trying to do? I'm trying to find an optimal control that goes from x0 to xt at time t, capital T. And I want to find the optimal way to go from x0 to xt in time capital T. It is my conjecture now that to do so, provided t is large enough. Okay, if t is large enough, then I will go from x0 to a point here with using control q, the maximum control q. Then I go along this line choosing the control us. Then at this point, just in time, so that I can reach exactly xt, just in time, I will leave this curve, this line, and use 0 control to come to xt. So what are the concepts here? First of all, we know we can easily compute this time. So we can easily compute this path. Other thing is I said t is large enough. By t large enough, I mean that t is larger than this 0d and larger than this ft. So d larger, t sufficiently large means t is bigger than sum of 0d plus sum of ft. By large enough, I mean that there is the c to g, the length of c of g is positive, and at least non-zero. I mean non-negative. Okay. If it exactly is the sum of these two, then you see what happens. You go up to here, and then as soon as you reach there, you have to come back again to get there. So I need to get there and maybe not stay there, or maybe stay there, but I need to be able to get there. See, if t is not large enough, then this is not a solution, because I cannot have this c of g. I do not have a line c of g, and I will tell you what to do later, because it's very easy to figure out what to do later. But let's now assume t is large enough. It is now my claim that that particular path is optimal. Well, it is optimal as follows. Here's the proof. Take any other trajectory, this trajectory. I'm taking the dotted line trajectory, then I'm going to go like there, and then I'm going to go like that. It's just any trajectory. It doesn't matter. I just took one. And I also took one just to make sure that I am something along this line for a while. It doesn't have to be. You can take any trajectory, arbitrary. Well, clearly, that trajectory will have some control, because I can easily find, once I find xt, I can, by using differential equation, I can also find out the ut that trajectory will accomplish. Okay, hopefully it is feasible. So we only take any feasible trajectory. Well, then we know that this trajectory crosses the other trajectory at this point, at this point, and this point. So now you see what happens. I want to compare this integral profit and the profit of this path. I already told you that if the integrand is negative, then the upper path is better than the lower path. Okay? That means that profit of this path is not as good as the profit of this path. I also told you that above this, the lower trajectory is better. So it means that the profit of this path is better than profit of this path. I also told you, well, I didn't tell you, but I can tell you now. If Ix equal to 0, then the two paths have the same profit. Why? Because the paths are coincident. They're the same path. And again, I can tell you that this upper path is better than the lower path because this is negative. So what is the conclusion? The conclusion is that I took an arbitrary trajectory and I found out that my profit of this trajectory is better than the profit of the arbitrary trajectory. I can do anything. I can take another trajectory like this. I can do the same argument, right? It doesn't matter. Any arbitrary trajectory, I can show that this was a better profit than that. And I have proved the optimality of the solution. So what I've done now here, I've done the following. I've done that I can find a stationary turnpike, and if my T is sufficiently large, then I can go to the turnpike and I can leave the turnpike and meet all the conditions and be optimal. Okay, so this is the solution of the problem. And it comes with its own sufficiency condition because everything is, the comparison lemma tells you that is a better solution. No convexity, nothing is required. This is the optimal solution. Now let's go back to what we didn't do. So we over here, we now know that there's a path where this Ix is 0. We know how to keep that path. We also know that, so there's a definition of sufficiently large and sufficiently small. And it'll be very clear once we get to these solutions. Okay, so now there are these so we are now sure that this path is optimal. We just proved it. Okay, this was the path where x0 is here and xt is here. Okay, and this is up to t1, and this is t minus t2. This is t2, and large enough means t is big. T should be bigger than t1 plus t2. That means bigger than this portion and that portion. Now let's go to this. What if xt is here? Well, then optimal solution is from here to here and then go here with the q. Same argument will work. The optimal solution is go from here to here to here. The optimal solution go from here to here to here, depending on where the xt is. So this means we have solved all possible problems as long as t is sufficiently large. Let's see what happens when t is not sufficiently large. Here's what happens. So when t is not sufficiently large, I can't reach the turnpike. Or if I reach it, I can stay there only at one point. So here is what happens. I go there, but then I know when to get here. If I was on a turnpike, that's how you get here. So I have a trajectory that if I'm above that trajectory, I cannot get here. So what I do is I go up to this trajectory and then go along that trajectory. That's the optimal solution. Again, you can prove using Green's theorem that's an optimal solution because every path that you take, you can compare. Another one, you go here and then go there. Again, the same argument. You can figure out when to get off. Same, if I have xt here and I have xt here and there's no upper bound q, if q is infinity, then I do an impulse control, come here, then an impulse control. I need to find out the value of the impulse control. It is not going to be the same as the null low error model because now u is multiplied by x. You know, in our equation of dynamics, the dynamics is more complicated. Yeah, the dynamics is like this: u times 1 minus x. So we need to use the formula in chapter 1 to find the dollar value of this impulse control. That means what you need to find out, is how much money you need to spend to go from x0 to xs by impulse. Okay, we'll do that shortly. So let's go back and see what we get. So we now started with Green's theorem, and we now shown by using a very good proof what we can do and solve each one of these problems and find the optimal solution. So everything is done. Just a little bit of history here, my personal history. I solved this problem at Carnegie Mellon when I was a PhD student. I was browsing through stuff to do, to look for stuff that I can do, and I found this Vidal-Wolf model. I was not a marketing student, but I found this model. And I found that they developed the model, but they did not know how to do optimal solution for this model. This was a model published in Operations Research. So I said, oh, this is a good control problem, so I should solve it as part of my thesis. So I solved the problem using maximum principle, but I am not able to do a sufficiency condition easily because it's not exactly a concave problem. And so at some point, I wrote a paper which was, I believe, publishable, but I was not completely happy with it because this was not, in a way, a complete solution that I wanted. And then I was a student at Carnegie Mellon, a PhD student. I spent about 2 years in my PhD program. So I was more or less done with my PhD in 2 years. I went to Stanford as a postdoc to work with George Danzig, who was a linear programming guy. You know George Danzig's name if you learn linear programming course. And there, while I was there, a course is taught in the electrical engineering department by a professor named Breakwell. And Breakwell was teaching how to solve problem of control theory by Green's theorem. And when I listened to the lecture, I said, my goodness, that is exactly the theorem I need for solving my Vidal-Wolf problem. So that day I came home and resolved my problem using Green's theorem. And within a day or two, I sent the paper to Operations Research. And they published that paper in Operations Research. What you see now, what you see in this book is that particular paper from Operations Research that I published. Okay, so that was my little story, but I did not do impulse control or anything, and this is something that I do now for the book. But anyway, so and then once I did the Green's theorem, published Operations Research, a whole slew of other people, I have some references in the book, a whole slew of other people applied the Green's theorem technique to solve many other optimal control problems. This was my paper was the beginning of, it was not Breakwell because Breakwell just started this and didn't solve any problem that I know of. But I was the first one to publish that, and then many other people use Green's theorem to solve their problems using the methodology that I used. Of course, I'm not the originator of the Green's theorem methodology, but I'm probably one of the applier of this technology. And so there are many papers cited in the book of this technique. Okay, let's do the impulse control quickly. So what do? We need to compute the cost of impulse at time 0. So this is at time 0. If in another time, you can do another time. But this was the formula in chapter 1. I begin at x0. I go to xs instantaneously at time 0. Okay. So what do? I use some control u. Let's assume a constant control u. Then formula, I solve the differential equation. The differential equation in epsilon time. So if I begin with x0, use a control u, then in time epsilon, the value of the market share will be x epsilon. This is the solution of the differential equation from 0 to epsilon. From time 0 to time epsilon using the control u. Okay, what is my purpose? My purpose is to go to xs. That means I want x epsilon to become xs. Okay, and I want x epsilon to become xs. I want u. This is u. So let's call it u of epsilon, because if I need to go to xs, I need some control u of epsilon. And then what I need is I want u epsilon to go to infinity and epsilon go to 0 in all of this formulation. Okay. And so using this in equation 1.23 in chapter 1 at t equal to 0, I have an impulse, which is the limit of epsilon go to 0 minus u epsilon times epsilon, because that's the amount of time. And that's the amount of control, that's the amount of time. So that's the amount of money that I use. Well, so now what you do is in this equation, I set epsilon to 0. I set this to be I, because that is my dollar that I'm looking for. That is the value of the impulse. That's I. So I set that equal to I. And I said u epsilon go to infinity. If I do all of this in this equation, this becomes x0 plus, because this is right instantaneously at 0 after my control. So that equation changes to this equation. You can do all of these here and you get this. Anytime you have this algebraic calculation that I go through without deriving this on the board, I will take forever. This is your job to go home and see if you can derive it, because they are straightforward. If you cannot derive it, then you can come to the next class or you ask Min to do it. So then I solve for I. You see, this is I. So if I solve this, I get this. So you see the cost of impulse of going from x0 to xs at time 0 is this. It's not linear anymore, okay? Because as x increases, the value of control decreases, because as x increases, then control only works for people who are not buying my product. So as x increases, the number of people who are not buying products shrinks. Okay, so the effect is less. Okay, and so as I go from one point to another point, as my x, so what is happening is as my x increases, see, as my x increases along this line, but of course, if it's epsilon, it increases along this line, then take a limit. So I can argue that as x increases on this line, the amount of control I use, its effectiveness decreases. And so I need to factor that in as I go up. And that is done by calculus for us. And you take the limit and you get this. Okay, so this is, in every case, it can be done. Any questions so far? We have one more thing to do, which is also important. This chapter is an interesting chapter with many things going on at the same time. Okay, before I go, so before I go further, I just want to mention that in 1983, I decided that I was working on stochastic control in finance. I wrote a book on stochastic control in finance. After my work in finance, I decided that marketing literature had no stochastic advertising problem, none. So my job was to at least solve one stochastic control problem in advertising. So I changed this problem to a stochastic differential equation by introducing some noise. And I found that I could not solve the problem. So what I did was I changed this 1 minus x to square root of 1 minus x. More story later when we do that. But when I changed it to square root of 1 minus x, I was able to solve the problem. I published that paper in 1983, and that paper is now known as the Seti model because there may be at least 30, 40 papers that have come since using that model. And because that model is so tractable and so easy to solve, that people use it. And then there were some empirical studies showing that the Seti model was at least as good or better than Vidal-Wolf model in explaining some data. And the person who wrote that paper was a former student at UT Dallas, former student of Frank Bass. And he subsequently became the dean of Kellogg Business School at Northwestern. He's currently a co-director of a school in Shanghai. I was talking to him a few days ago because he wants me to go to Shanghai and visit his institute there. So 7.37 that I assigned you for homework is the solution of the Seti model. Okay, it has a closed form solution, and it is a deterministic version of it. The reason I assigned that is because we will do the stochastic version of the Seti model in stochastic chapter like 12 or 13 or whatever. We will do that then. Okay, so that is a little aside. Now I'll go back to our chapter. So the next thing we need to do is what happens if Q is too small. So what happens is when Q is too small, it means that Q is smaller than US. It means I cannot follow the turnpike. That means I can go to the turnpike, but I cannot continue to stay there, right? So what do I do? And this is where I got this idea that the MRAP, or the most rapid approach path, is not optimal. What is optimal is something called the nearest feasible path. And if you look at my paper that is cited in this chapter, the title of the paper has the nearest feasible path term in it. And I told you the story why I regret that particular aspect. Okay. It has something more than that. That paper did not get recognized for a long time, but I also made another innovation in that paper. I made an innovation in that paper saying that there are some points where there could be two optimal solutions that are equal. And such points were recognized in my paper in 1977 for the first time. But since that paper was never recognized by many people, in 1978 or 79, a Russian guy published a paper exactly showing these two optimal solutions starting from one point. And subsequent literature started calling those points Skiba points. And many years later, I realized somebody was talking to me about it. I said, Skiba point. Well, I did that before this guy. And so people tried to change that name from Skiba point to some other points. In Wikipedia, they call it a DNSS point with the third letter S stand for Seti, but that did not catch either. So I decided, and some other people, anyway, but I decided that they should be really renamed as Seti Skiba point, because Skiba was not the first one, Seti was the first one, but you can keep the term Skiba. So I decided to call them Seti Skiba point. In my book, if you search for Seti Skiba point, there's an appendix section on Seti Skiba point. I did not put in the main body, although some of my friends wanted it so. So by not having a proper title, I also did not get named for Skiba points. So anyway, It should have been simply Seti points, not even the Seti schema point, but it is not so. Okay, so there's a lesson to it in terms of how do you create a good title, and also, and there's also a lesson that I'm not a very good salesman. Okay, so what is when a queue is too small? When queue is too small, I cannot follow the turnpike. So I must figure out what to do and how to solve the problem. And this is the section where I solve the problem. Because there may be not enough time, or there would be enough time, I think, but let's go to a big picture first. Excuse me, let's see what my idea was. So I'm trying to guess a solution and then solve it, okay? And this is, so I go to the solution first. Here's my problem. It's the same problem with all levels, but this is difference. I now have a 0 less than u less than q instead of u bigger than or equal to 0. And I'm now saying q is small. Q is large means everything works. Okay, q large means we already solved the problem. Q small means what to do. So I'm going to go straight to the results first. So here is the turnpike that I actually cannot follow because I don't have enough control. Remember the example 4 that you did not solve, or most of you didn't, because 3 divided by 2 was not enough. You needed 2 to get to the curve at time 1. Now that 3 by 2 was too small, right? For that solution in the book to work. So now Q is too small. So I cannot go there. I can go there, but I cannot stay there. So what do I do? Well, clearly, if I cannot follow this, I can follow a path that uses the control Q because Q is small. So this is the path X bar, which I can follow. And that I can use chapter 3 to find the long run stationary equilibrium. So I can find that. That is not a problem. How to get there? What is the optimal solution is important. Okay, that is the subject of this chapter, this section. This. So somehow this is what I need to follow, not this one. Now, if the optimal solution was the most rapid approach path, then you would think that most rapid approach path means I would use control 0. So this is my x0. I will use control 0 all the way. I may come here or I may approach here. That is not important. What is important is to get to this path or approach this path fastest possible. MRAP means fastest possible. The fastest possible is if you have a 0 control that you can use, then the 0 control will be the fastest way to get to X bar. X bar is our new turnpike, not this one. This one. Turn out that is not the case. Okay, if you're below, everything's fine. If you're below X0, you use Q, and you can only approach this X bar because you can never get there anyway. So you will simply approach this path, and so MRAP is good, it works, fine. But what happens if I'm here? Well, the idea now is to reduce the amount of deviation from this guy. Remember I gave you that picture of time-dependent turnpike, which was more complicated than this one. And there, of course, I just gave you the idea. Here, I'm actually solving it. So the idea is to have reduce the deviation from this side. Well, if I use Q control all the way, then the deviation is this given by this triangle here and this big area here, all the way to infinity. So the deviation is that and that. That is the deviation. But I have no control. I just use Q and this point comes wherever it comes. I have no control over it. But I can use the control this way. Here's what I can do. So look what I'm doing now. This is my X bar. This is the turnpike from which I need to reduce the deviation from, because that is the actual turnpike. This is the turnpike that I can only. This is a feasible turnpike. This is the ideal turnpike. Okay, so this is my X0. What am I going to do? I'm going to create a path so I can decide when I can reach this some path. So I'm going to use a zero control for some time up to this point, some X hat. And then I'm going to switch to Q. And now I have a control of where I get to this point. Okay. Now I need to find the optimal place. And what is the optimal place? Now look at the deviation. So what am I deviating? So if I go this, look at the deviation from XS. That path I'm deviating. So remember, I'm going to go 0 and then I'm going to go to Q. That's my path. So what is my deviation? First deviation is going from here to here. And the second deviation is from yellow line, this line. This is square one. So this is another deviation, right? So my deviation from this path is this. Okay. What if I use all the way 0? So you see my deviation now is this big path. It is going from here all the way there and there. And on this side, it is a little bit less than mine because mine is here. It is little less than mine, but on this side is much bigger than mine. So by manipulating this, I should manipulate in such a way so the deviation from these paths are minimized. By that, I mean that the cost associated with the deviation is as little as possible. And that maximum principle will give it to you. If I can solve the problem using maximum principle, then I will get an optimal solution anyway. And that is how I mean by reducing the deviation, because I get the optimal solution, which is the most profitable one. So the solution deviation has to be as little as you can get. Any other path will have more deviation because more cost. Okay. Okay. So that's what I do. So you see, by creating this, I did that. And then once we get away from the big picture, we can do the nitty-gritty and solve the problem. But notice what is going on here. This is the fastest approach to this path. And then I can go here. So the fastest approach says go all the way to here and then stay there. My approach is go 0 up to here and then use the Q. No, use 0, which is this, and then use the Q. And the fastest approach is go 0 here, then use Q. Fastest approach is not optimal. My is optimal, and that is the nearest feasible path of this. This is the fastest approach to the turnpike, which is this one. But that one is mine is not the fastest approach to turnpike. Mine is the nearest feasible path to this ideal turnpike. So that was the idea, that to get the nearest feasible path to ideal turnpike. And that was my terminology. It was a good terminology. Okay, so now we solve the problem using the maximum principle. So how do I do that? First, this is easy to do. We already know X bar. This is using the chapter 3 definition of turnpike. And now we have to put mu. You need a mu also because it's a 4. Turnpike will have 4 things. You will have x lambda, u, and mu, because mu is a constraint on this control that u should be less than or equal to q, and we are at the boundary q, so we can have mu. So I have x bar, lambda bar, and we have a mu bar. So we have all of those quantities that we know. And then what we need to do is we need to get to this point. We need to get to this point, x hat. See the x hat? We need to find x hat. Finding x hat is same as finding T1 because this is zero control that goes from there to T1. And from this point on, I should have the turnpike. I should have x bar. No, from this point on, no, yeah, from this point on, this quantity here, I should have x bar, lambda bar, mu bar, whatever. Okay. So basically it's fudging. So I need to fudge all these things. And to do this fudging, I have to do an x hat. And so you see the nearest here, the word nearest feasible path. And that paper is cited is 1977B. This is exactly the point where I also discovered what is so-called Seti schema point, but never named them. Okay. So when x0 is bigger than xs, what happens is, let us find x hat and mu bar such that wx hat lambda bar, which is the switching function, is 0. So if you do that, L sub u, which is the Lagrange multiplier, would be exactly this, and I will have a mu bar and x hat. So I can find x hat in terms of this, and once I have x hat, I get to the solution of the problem, and I can satisfy. Okay, once I have x hat, I can find T1. I can solve lambda dot, and then once I can solve lambda dot, I need a lambda dot so that the lambda T1 is exactly lambda bar. So I go backward. So what I do is I have a lambda T1 equal to lambda bar, and I go backward. Remember, at each point tau, between this point and this point, I know everything here. But on this one, I need to find out the x lambda. I know what the x trajectory is, x tau, because it's 0, so I can create that. Lambda, I can do lambda bar, and I can go back, so I can create the lambda trajectory. I can create the lambda trajectory, and then I should have a switching function which is less than 0, so that control is 0, optimal control is 0 all the way. And so all of these can be done. So once I solve the lambda equation, I get the lambda tau, I can get the x tau, and then I can get the w tau, and everything works out. Okay, and that wt1 has to be exact. So I want wt1 has to be exactly equal to 0, because after that, it's a singular control. Or it is a control, not singular control. It's a control Q, and it is the long-run stationary equilibrium. But here, W will change. It'll become negative and become 0 exactly at this point. So all of that, once you have the solution guessed, you need to figure out how to patch things. Just like in example 4, the test 4. Once you have a kind of a guess, proper guess, you can actually do the maximum principle and prove that your guess is optimal. So this is basically what is done here. It's a little bit more complicated than example 4 or the question 4, but it is a complete, definite picture of proving that it is not MRAP, which is optimal in a situation like this. It is actually something called the nearest feasible path that is optimal. Questions?
Excuse me, Professor. So what is the equation of T1, which is the switching point of U between 0 and...
It's right here. You see, so let's now go through the maximum principle. Yeah, maybe I did a little bit too fast. So we have a Q small, we have a Hamiltonian, right? That's no problem, right? And
Yes.
then we have a Lagrangian, right? Hamiltonian plus mu times Q minus U, right? So far, so good?
Yes, that's clear.
Okay, then we have a lambda dot, and we have a complementary slackness condition. So maximum principle has to have all of these conditions satisfied, right? That's what we need, right? Okay, so now what we do? we have a control which is bang bang, 0 Q, W2, there's a switching function, right? The switching function is exactly R times lambda times 1 minus X minus 1, right? So far, so good?
Oh, yes, yes.
So now what I need is I want this switching function, because switching function has to go to 0 exactly when the control switches from 0 to Q, right? The
Yes.
switching function has to become 0 at that point, because if it was negative, then it has to become whatever, okay? So here's what happens here. So I got X bar, I got lambda bar. I need a point X hat. You see, switching function at that point will be W of X hat lambda bar, which is going to be R lambda bar 1 minus X hat minus 1. I want that to be 0, right? So I want lambda to switch to lambda bar and X to switch to X hat and W go to 0. Okay, so this W is 0 and that W, that the Lagrange multiplier, this is equal to 0. But that one, we already know what mu bar is, right? Because this we can do by chapter 3 formulation that we had, right? So now that equation gives us the X hat. You see that? We know lambda bar. We know lambda bar is right here. And we know now X hat. Once I have X hat, I can find T1, right? Because what is T1? If I give you X0 and I have to go to X hat using 0 control, then it will tell me the amount T1 at which X0 will become X hat, right? That's just a simple differential equation solving with U equal to 0 and end condition X hat, and I give you the T1 equal to this.
Oh, I see. I got it. Thank you, Professor.
Yeah. But the trick is to say, go very fast, but don't go fast all the way. Because if you go fast all the way, then you are creating a more deviation from this ideal turnpike, which is not feasible. But you see all the one that you're creating all the way to infinity. Whereas by doing what I'm doing, I create less so, because what maximum rapid approach math is trying to get to X bar as quickly as possible. But by going as quickly as possible, it creates more deviation from the ideal path. Whereas by going initially using X0, see, 0 is not allowed. I mean, by using 0 not all the way, I do this. So what I'm trying to say is that's what MRAP would do, but this is not optimal. This is what is optimal. The other one is it's also not optimal. If you use Q all the way, that's also not optimal, because that is the slowest way to get there, right? That's saying just use Q all the way. But that is okay if Q is if it is, yeah. This is only showing for X0 less than X hat. For X0 bigger than, oh, I'm sorry. I'm sorry what I'm saying. What the intermediate step is this. If X0 is not too far, right? Then this is fine. And that's exactly what's happening here. If X0 is if X0 was X hat or below, I don't need this 0 portion, right? If X0 is too large, I want to quickly get somehow in the beginning to some level, right? So what we're trying to show here is the following. We're trying to show that you can easily show that if I'm below X bar, this is optimal. If I'm close to X bar, then this is optimal. But how close depends on where X hat is. And that basically is a $64 question in this problem. Once you know X hat, you know everything. So finding the X hat is the main aspect of this problem. Okay, this is some X hat. See, there is some X hat, then that works. but we don't know what x hat is yet. It only comes when we solve the problem. So once you have x hat, you can create this path and that path. Those are the two. And this one create this has everything. This picture has everything. It has even this one. It has this one because this picture concludes that that if my x0 is below x hat, I don't need this 0 portion. It's clear, right? Because remember, it's an infinite horizon problem. So that problem can begin here. A problem can begin here. So if I at this time t, optimal solution is exactly this, right? So at any time t here, if I begin the problem here, the optimal will be this yellow line. So I can simply say that if I begin at 0 at this point, then that yellow line will simply start from here and it will just go like that. It's simply a translation of the yellow line from this point to that point, right? So that picture carries this picture with it. You don't need this picture but it's good to have in 2 steps. So this is very similar. If you look at the picture that we had earlier, I mean, the idea that I had here is I never. This is the only place this picture is published. It's never published in any other paper that I wrote. You can sort of see here that I don't want to go all the way up to here. I get off earlier. So this is getting off side. It could also be applying, similar thing can also apply to how to get onto the turnpike. The idea is similar again, that the deviation that you want to minimize in terms of dollar is the deviation from the ideal turnpike, which is not feasible. So here see, this part of the turnpike is not feasible, right? This part of the turnpike gives you this control, which is not feasible. So I have to, in any case, I can use 0 control here. But why should I use 0 control only here? Maybe I can go earlier. So that's kind of the idea is give yourself a little control, which allows you to obviously at an extreme, this solution will be optimal. If you do this, depending on the curve, at some point this C could be exactly A. It's possible, but that is just that's just coincidence. You know, it's not a general setting. Any other question before we finish? Okay, if there are no more questions, we will please read chapter 8. I think chapter 8 is not that long, so I would also suggest that you may also want to read part of chapter 9, because I think we will probably go to chapter 9 next week. I'm not giving any exercise homework from chapter 9, but I would suggest you read at least half of chapter 9, because chapter 8 is a discrete time control theory chapter. Most of the book is on continuous time. Most of the work gets in continuous time. Discrete time, generally speaking, in many cases, can be done using discrete time and continuous time. There are some issues, but those issues are not something that we worry about. There's some mathematical issues between continuous time, discrete time. Again, we don't worry about that. But in almost all cases that we would worry about, discrete time and continuous time will give you a discrete time, and then more or less you can go that route.